Alright, so as we inch closer and closer to our culminating event of, properly curve sketching with all the components and aspects of the wonderful world of functions, we're first going to get some practice here identifying points of inflection and intervals of concavity for a slew of different functions. So let's say we have this fifth degree polynomial. The first thing that we'd obviously want to do if we're going to talk about points of inflection is we need to get to the second derivative. So f prime of x is 15x to the fourth minus 20x cubed. That if we derive a second time gets us 60x cubed minus 60x squared, which if we factor gets us here. So we can see that we have potential points of inflection at x equals 0 and 1. 0 and 1. Now if you think back to our test for concavity, we are going to be looking at the second derivative. So when we're selecting values here, we're going to resubstitute them into the second derivative. And now I'm not concerned with the output, I'm just concerned with the sign. So I'm going to have negative 1, f of 2, and f of 0.5. Okay. You can substitute here, but I suggest always substituting at your last most factored form of the expression. So negative 1 will turn positive here, and negative 1 minus 1 is negative 2. Therefore, we will have a negative output. And if we replicate that process with 2, positive 2 minus 1 is positive, so we'll have a positive. So clearly, we're only going to have one point of inflection, right? Because if this is negative, there's no change here. If it's positive, there's no change here. 0.5 will still be positive here, and negative 0.5 minus 1 will give you a negative. So we're going to have this negative, positive behavior from the second derivative. So there's no change at x equals 0, but we have this change from negative to positive. So we can say that x equals 1 is a point of inflection. But, so we got this. We have our intervals of concavity, which we can see from negative infinity to 0. And 0 to 1. Our function will be concave down. And from 1 to infinity, our function will be concave up. So, nothing really too different than what we've already been doing with first derivatives. However, we have a nice, beautiful, continuous polynomial here. What happens when we change that from a beautiful polynomial and advance into something a little bit more dense, like a cube root function? So once again, same setup. Let's make our way to the second derivative. Don't worry, you will get this fast soon enough. Oops, messed that up. Look at me. 5/3. This should be positive. This should be 10/9. And now we should have negative 1/3. Okay, sorry for that. So if we do a rewrite here, we can see that we have a rational function for the second derivative, which it will be undefined at x equals 0. So we obviously need to look and examine the behavior for when x is greater than 0 and when x is less than 0, because we know that this function, since it is a cube root, will be continuous across the entire domain of real numbers. If I substitute in positive values that are greater than 0, this will have a positive output. And if I substitute in negative values for this function, it will have a negative output. Thus, since we do have a sign change on the second derivative, we can say 0, 0 is a point of inflection. That should be a C. You can also say that the function is concave up and concave down along those intervals. So before we proceed, I do want to make a mention, right, because of this example in particular. Just like these zeros and undefined values of the first derivative lead us to local max min values the same occurrence in the second derivative can lead us to points of inflection but what if I were to tell you that we could make this entire ordeal, right, the extrema, the concavity, the points of inflection, a one-stop shop situation? I bring you the second derivative test. Now, full disclosure, I like doing them separately. That's just me. But if you're somebody that's hung up on this idea of efficiency, by all means, this will be for you. So let's see the critical point of f of x. If the second derivative exists, then three things can happen. Right? We can have obviously a situation where that derivative is greater than 0. We can have a situation where that derivative is less than 0. And we can have a situation where that derivative equals 0. So, in the event where the second derivative is greater than 0, we can say that f of c is a local min, and the graph is concave up. In the event the second derivative is less than 0, we can say that f of c is a local max, so the graph is concave down. In the event where it's equal to 0, I don't tell you nothing. Don't tell you nothing. So in that case, you gotta go back and do the first derivative test anyway. That's why I like doing them as separate processes. But let's take a look at one of these. Let's see what this looks like in action. Analyze the critical points of f of x, and gone are the days of our nice beautiful polynomial functions. Enter this juggernaut. So we're clearly going to have to make our way to the second derivative. Bear with me. To take the first derivative, we're going to need a product rule. First times the derivative of the second, derivative d to the x, d to the x, plus the second times the derivative of the first. do it or float your boat here. Many of you will want to simplify this first. You're more than welcome to. But remember, you need to analyze the critical points. The critical points exist in the first derivative. So we must first set that bad boy equal to 0. Okay. In doing so, we are going to wind up with a situation where, if we factor this out, we're going to get e to the x, 2x minus x squared plus 2 minus 2x. So these actually wind up canceling each other out, which makes our life a little bit easier. This is still equal to 0. And we have e to the x, 2 minus x squared equals 0. Well, there's nothing that we can substitute into x here that will result in a value of 0. So we really don't even have to worry about that. Just this. And we can see that x will equal the positive or negative square root of 2. That is our critical point. Let's see. Equals that. I'm, from this point, going to now take the second derivative. So let me rewrite this function so we have it as a reference. 2 minus x squared so first times the root of the second plus the second times the root of the first. So literally the first derivative. We can do the same thing here, but it's not necessarily needed. But if you're one of those people, I will definitely help you out. 2 minus 2x minus x squared e to the x. So now once again we want to check these critical points. So positive root 2, negative root 2, substitute into this function. It's going to look a little gnarly. Now we're going to have e to the root 2, e to the negative root 2. And once again, we're not concerned with output, we're just concerned with the sign, the behavior of the second derivative. These are both going to be positive because that's only a rational value. So we have 2 minus 2 root 2. Right here I already have a negative minus the square root of 2 squared. Those will cancel. 2 minus 2 is 0. So this overall will be less than 0, which will yield a local max. And here, 2 plus 2 root 2 minus negative root 2 squared. That'll turn positive, cancel, cancel. But we have a positive compared to the negative here, right? Because these will wind up canceling out again. So this will be greater than 0, indicating a local min. Okay. And then we would obviously have to check in between these critical points for points of inflection. Or no, sorry, not points of inflection. We'd have to re-solve this expression, set equals 0, to solve for points of inflection and concavity. But that's not the purpose of this example, but things that we're going to have to do. So if you like to kill two birds with one stone, second derivative test for you. If you don't like to do that, like myself, first derivative test, then second derivative test. I'm going to leave you with one to practice on your own. That is a nice continuous polynomial. And I'll leave you with a little bit of solutions to wet your beak. There will be a local max, but it's not going to be as straightforward as you think. And there will be a local min. And that's where we will pause. At this point in time, we've done the first derivative test, we've done the second derivative test, we've talked about inflection points, we've talked about critical points, we've talked about concavity. In our next two-part video, we will talk about what these things look like graphically. See you there.